Hello dear students, welcome back to the course of Mathematics-1. Today in this session, we start with Taylor and Maclaurin series. As we know that Taylor series is nothing but special case of the power series. So in mathematics, the Taylor series of a function is an infinite sum of terms that are expressed in terms of the function's derivative at a single point. For most common function, the function and the sum of the Taylor series are equal near that point. The Taylor series are named after Brooke Taylor, who introduced in 1715. If the 0 is the point of the derivative are considered, the Taylor series is called Maclaurin series after Colin Maclaurin, who made an extensive use of this special case of Taylor series in the 18th century. Taylor series is a polynomial of degree n that is called nth Taylor polynomial of the functions. Taylor polynomial are approximation of a function which become generally better when n increases. Now let's have a look at the first theorem Taylor series. If the function f of x possesses derivative of all order at a, then fx can be expressed as f of a plus x minus a divided by 1 factorial f dash at a plus x minus a whole square divided by 2 factorial f double dash at a plus and so on. And this can be expressed as a summation. So summation starting from n is equal 0 to infinite x minus a raised to power n divided by n factorial into nth derivative of function f at a. So now let's have a proof of this theorem. So first point, we have to consider the power series expression because this is the special case of the power series. So let us assume that the power series expression of the function f of x. So here a0 plus a1 x minus a plus a2 x minus a square plus and so on. Say equation number 1. But here ai is nothing but constants, where a is nothing but center of the power series. Now, to express the Taylor series representation, it is required to determine the constant a0, a1, a2, a3 and so on. So for that, we have to consider successive differentiation with respect to x. So let us first consider differentiation with respect to x. So we have f dash x is equal to a1 plus 2a2 x minus a plus 3a3 x minus a whole square plus and so on. Say equation number 2. Now again successive differentiating with respect to x, we get f double dash, then third derivative and so on. Now we substitute all these values in the equation 1, 2, 3 and 4. So here if we put x is equal a in the first equation, so what we get, f of x is equal a 0. But when we put here x is equal a here, so f dash at a is equal 37 and f double dash at a is nothing but 2a2 and a third derivative at a is that will be 6a3. So after representing all these terms, we get a0 that is f of a, a1 f dash a, a2 that is f double dash at a divided by 2 factorial, a3 third derivative of function of f at a divided by 3 factorial and so on. So in general, we can say an is equal nth derivative of function f at a divided by n factorial. Now we substitute all these values in the equation number 1. So this is our considered power series. So when we substitute all these values a0, a1, a2, a3 and a4 and we get here that is known as Taylor series representation. So this is our standard form. So this is whenever we have given that function f of x, so that function can be expressed in power of x minus a. In other words, we can say function can be expressed or estimates about any near point, and that is exactly our Taylor series. Now let's have a look at the different forms of the Taylor series. So here this is our standard form, but if we put x is equal a plus h, that means x minus a will be h. So then our standard forms becomes this one, that is f of a plus h is equal f of a plus h divided by 1 factorial f dash at a plus h square divided by 2 factorial f double dash at a plus and so on. And this is the Taylor series in the neighborhood of a point A. So, or in other words, we can represent if A is replaced by only x, then the form will be f of x plus h is equal f of x plus h divided by 1 factorial f dash at x plus and so on. And again, this is our form 1, but again, if we replace a by h and h by x in the form 1, we get the Taylor series in power of x. So, whenever you have given that any function, and again in that case you can represent Taylor series expression in power of x. For example, you have given that the function f of x plus h is equal sine of x plus h. So, in that case you can represent sine of x plus h in power of x, and that formula will help you to represent it. So, again if we put a is equal 0 in the equation 5, so this is our equation number 5, equation 5. So, if we substitute a is equal, that is 0. So, our Taylor series becomes Maclaurin series, or in other words we can say Taylor series about the point a is equal 0 is known as Maclaurin series. And again, after next lecture we will discuss about the Maclaurin series. So, this is our formula, f of x is equal f of 0 plus x divided by 1 factorial f dash at 0 plus x square divided by 2 factorial f double dash at 0 plus and so on. So, yeah, suppose we have given that any function. So, if we represent Taylor series representation about the 0, we call that is Maclaurin series. So, here this is the Maclaurin series. Before considering example, let us look at the some prerequisites. So, these are the basic formulas already you have studied in the 11th and 12th. So, this is first d by dx of any constant, that will be the 0, d by dx of x raised to n, that is n into x raised to n minus 1. Third, d by dx of a raised to x is equal a raised to x into log a with the base e. D by dx of e raised to x, that is going to be a into e raised to x. Fifth, d by dx of log x 1 by x. Next, d by dx of log x to the base e. That means that can be written as log x divided by log a. So, d by dx of log x divided by log a can be written as log a is nothing but constant quantity. So, we can take outside this derivative. So, 1 divided by log a into d by dx of log x, but we know that d by dx of log x is that is 1 by x. So, our answer will be 1 divided by log a into x, that is our standard form. So, then d by dx of sin x, that is cos x, again d by dx of sin x, that will be first derivative of sin, that is the cos, but derivative of ax, that is going to be a only, and this is already we can say we have used the derivative of the composition of the two functions. Next we have d by dx of cos x, that is minus sin x, d by dx of cos ax, that is minus a sin ax, d by dx of tan x is equal sec square x, d by dx of sec x is equal sec x into tan x, d by dx of cot x is equal minus cosec square x, d by dx of cosec x is equal minus cosec x into cot x. But here we can observe that first 8th number formula, that function start from c. So, cos function is there, here cot function is there, and cosec function is there. But when we consider derivative, so derivative will be always negative, and that thing we will keep in mind. Next we have d by dx of sin inverse x. These are the inverse trigonometric function, and that you all know. So, I am not going to discuss all these formula, but you all are familiar with these formulas. And d by dx of sin hyperbolic x is equal cos hyperbolic x, and d by dx of cos hyperbolic x is equal sin hyperbolic x, and this is the product rule for the derivative. So, d by dx of u into v, but here u and v are function of x. So, in that case derivative becomes u into dv by dx plus v into du by dx. And next one we have the division rule, d by dx of u divided by v. So, first we can say denominator. So, this is the denominator square, denominator v as it is, then derivative of the numerator, that is du by dx, minus numerator as it is, that means u is there, and derivative of the denominator, that is dv by dx. So, these are the basic concept already you have studied in standard 11th and 12th. So, now let us have a look at the table, that is the trigonometric table that will help. So here you should keep in mind that if I sin 90, then answer will be 1. But if I say cos 90, so answer is 0. That is radian. If I say sin pi by 2, so answer is nothing but 1. If I say cot 3 pi by 2, so answer should be 0. And then all the values you will have to remember. So I'm not going to discuss all these values here. So now let's have a look at the example which are based on Taylor series in power of x minus a. So this is the first question. Find the Taylor series of the function f of x is equal x raised to 5 plus 2x raised to 4 minus x square plus x plus 1 in power of x plus 1. So your given function has degree 5. So whenever we consider the derivative. So now first question arises, how many terms we should consider for this expression whenever we consider Taylor series representation. So whenever we have the given function as a finite degree, so in that case we will consider higher than 1 degree. That means fifth degree is there, so we will consider sixth derivative and that will be the 0. Suppose you have given that the function f of x is equal x square. So in that case first derivative will be 2x, second derivative that will be only 2 and third derivative will be 0. So we have the degree is 2 and the third derivative is what exactly, that is 0. So whenever the polynomial functions are there, so we consider ordinary derivative until you get the 0 answer. So let's have a look solution of this question. So first we want Taylor series in power of x plus 1. So first we compare x plus 1 is equal x minus a. So we get a is equal minus 1. So this is the Taylor series representation standard form. But if we substitute a is equal minus 1, so our forms will be f of x is equal f of minus 1 plus f raised to minus 1 x of minus plus. That means f raised to minus 1 x plus 1 plus f double raised to minus 1 divided by 2 factorial x plus 1 square plus and so on. That means we have to determine f of minus 1, f raised to minus 1, f double raised to minus 1. So let's have a consider first function f of x, that is x raised to 5 plus 2x raised to 4 minus x square plus x plus 1. But if we consider f of minus 1, so answer will be that is 0. Again we find success in differentiation. So first derivative, so f raised to minus 1, answer is 0. F double raised at x, and in that case we consider particular point x is equal minus 1. So we get f double raised at minus 1 is equal to third derivative at minus 1, that is 12. Fourth derivative, that is 120x plus 40, but at particular point minus 1 we get the minus 72. Fifth derivative, that will be the constant. And here we get the sixth derivative, that is 0. So fifth degree of the polynomial is there. So we get the sixth degree of the derivative will be 0. So here at particular point also it will be 0. So now we consider all these value in the Taylor series expression. This is our standard form. Just put here a is equal minus 1. Our forms become this one. But now we substitute whatever we have found at the derivative. So if we substitute all these value and we get this form. But after simplifying these terms, we get f of x is equal x plus 1 square plus 2 times x plus 1 raised to power 3 minus 3 x plus 1 raised to power 4 plus x plus 1 raised to power 5, and which is required Taylor series. That was our claim. So now let's have a look at the example number 2. Prove that ln x is equal x minus 1, x minus 1 whole square divided by 2 plus x minus 1 raised to power 3 divided by 3 plus and so on. So from this question you can say that LHS is equal RHS. But RHS is exactly what? Left hand side we can say ln x, that is a function. Right hand side is nothing but a series. So what we can assume that about the Taylor series, and if function is same as sum of the terms and which are equivalent at particular point, that we can say. So here if we assume that on the left hand side x is equal 5, and if we put right side x is equal 5, and if we add all these terms and we get the both the answer, that is the approximate. I can say this is the application of the Taylor series. So in that case, suppose I want to express this form. So in that case I have to just recall that what it is exactly. So we can say it is the expression in power of x minus 1. That means I have to use the Taylor series expression about a is equal 1. So here we consider the function f of x is equal ln x, and we find the Taylor series expression about a is equal 1, and that will be our final representation, and that is we want. In other words, this question can be asked, find the Taylor series of function f of x is equal ln x in power of x minus 1. Also we want to estimate at the particular point 1.1. That means find the value of ln 1.1. So here, so let's have a look at the solution. Here x minus 1 is equal x minus a, so we have a is equal 1. So here fx is equal ln x, so f of 1 is equal ln 1, and that is we know answer is 0. First derivative, that is 1 by x, so first derivative at 1, again answer 1. Second derivative, that is minus 1 divided by x square, so second derivative at 1, that is minus 1. Third derivative 2 divided by x cube, so third derivative at 1, that is 2, and so on. So after finding all the successive differentiation, we substitute all these value in the standard forms of the Taylor series, and after putting all this value we get this expression, and this is what exactly after simplification we get. F of x is equal x minus 1 minus x minus 1 whole square divided by 2 plus x minus 1 raised to power 3 divided by 3, and so on. But here what was the function? Function f of x is equal ln x. So we have ln x is equal this expression, and that is we want to prove that. And if we consider x is equal 1.1, so we can estimate the function ln 1.1. So we are going to estimate here. So just replace x by 1.1, and after simplifying using the calculator you will get the 0.095275, but which is approximate 0.0953, correct up to 4 decimals. So in this lecture we have studied about the first theorem, then we have recalled the some basic formulas, then we have discussed some basic different forms of the Taylor series, and based on that we have seen first case of the example. Thank you for watching.